Here we have a bike wheel with outer radius 36 centimeters. So let's start identifying these different quantities. The radius is 36 centimeters, and hopefully we are comfortable with realizing that centimeters is probably not the best unit. So let's change that right away into meters. And it has an initial angular speed of 5.2 radians per second. That's omega initial. The wheel's speed increases to 9.8 radians per second, so that's going to be omega final. And the angular acceleration has a magnitude of 0.68 radians per second squared, so that's going to be alpha. In other words, we know what omega final is, we know what omega initial is, we know what r is, and we know what alpha is. And the question here is, how much time elapses? So if we go to our kinematics equations, we need time. So this equation at the bottom is not going to work because it doesn't have time. The no time equation was not going to work because it doesn't have time. But we have a time there and a time there. We got some times, a bunch of times here. And we've got r, alpha, omega initial, and omega final. If we're looking for time, and I know what alpha is, and I know what omega final is, and omega initial, I think I'm going to use this equation right here without this middle portion. Alpha equals omega final minus omega initial divided by time. We need to solve this for time. If we multiply both sides by time and divide both sides by alpha, I think we're going to get an expression that looks like this. You convince yourself that that's okay. And now let's put the numbers in. Omega final is 9.8 radians per second. Omega initial is 5.2 radians per second. I'll go ahead and put the units in there. And we're going to divide by the angular acceleration, which we're told is 0.68 radians per second squared. Now, it might be a little tricky for you, but I think if you think long enough, you'll be able to realize that if you take radians per second and divide by radians per second squared, you do end up with the unit seconds. When I did that, I got 6.8 seconds. From the time when we tune in till the time we tune out, it's 6.8 seconds. Now let's find the angular displacement that occurs during this time. So the angular displacement is going to be theta. This equation is clearly not going to work because it doesn't have theta in it, but we need theta. So if I circle the thetas that are in here, in fact, this one has theta as well. Now we know the time, and we know omega final, we know omega initial, we know r, and once again, pretty much any of these equations except for that one, because we don't know the arc length yet, but any of these three will get the job done for us. As I mentioned in an earlier video, the only issue is that if you use this one down at the bottom, or if you use this one here at the top, you must use a time. And we just calculated a time. Assuming we've calculated that correctly, if we use those equations, we'll get the right answer. But it's good scientific practice to go back always to the quantities that we are given. And we were given omega final, we were given omega initial, and we were given alpha. So I'm going to use the no time equation to find this angular displacement. Omega final squared is equal to omega initial squared plus 2 alpha times theta. Shall I show a little work here? We're going to subtract omega initial from both sides. That's going to equal this expression. And then to find what Theta is we're going to divide both sides by 2 and divide both sides by alpha, which is going to leave us something that looks like this. So let's put the numbers in. We've checked the units ahead of time, so I'm going to be a little bit lazy and I'm not going to write the units this time. Omega final is 9.8, got to square that, minus omega initial, which was 5.2, need to square that, need to divide that thing by 2, and we also need to divide it by the angular acceleration, which is given as 0.68. You type that in, and you're going to get an answer that looks something like 51 radians. How about the next part? Here the question is, the wheel goes around how many times? This is one of those cases where we are going to find useful the use of a previous answer to calculate the question at hand. We just found that the angular displacement is 51 radians, and the question is, how many revolutions is that? Or rotations, I guess, in terms of a wheel. How many times around is 51 radians? We're supposed to know that for every one go-round, it's 2 pi radians. Essentially, this number down here, isn't it? 2 times pi is about 6.28 radians, isn't it? Because pi is about 3.14. So 51 divided by 6.28, 8.1 revolutions. 8.1 times this wheel has gone around. Last one for this video, what linear distance is covered? The linear distance is the same as the arc length. Whenever a wheel rolls, by the time it has rolled around once, every point on the rim of the wheel has touched the ground, and the linear distance that has been covered is the circumference of the wheel. So the linear distance that something rolls, assuming it doesn't slip, is the same as the arc length. Well, the only equation that we have that deals with arc length is that one right there. So the distance that we want is the radius of this wheel, which you might remember was given as 0.36 meters. And then we want theta. Theta has to be in radians, and so we're going to want to use this number right here, 51 radians. We're not going to use the 8.1 revolutions. And when we calculate that, we're going to get to 2 significant figures, which is what everything was given as, 18 meters. You might be a little bit concerned about the unit, meters times radians giving us meters, but we said early on that a radian is kind of a nothing unit. It's kind of a unitless unit, but we often don't feel comfortable saying nothing, so we say radians. Well, in a case like this, when you multiply meters times radians, the radians really disappear, and you end up with just meters.